Section 11.8 is about systems of differential equations. And we'll put this in a population model. We'll look at robin populations again, but this time we're going to call the robin population R instead of P. P for population here, or in the previous model. Here, R is for robins. It's the robin population. In whatever units you want to use, like thousands of robins or something. I won't specify the units. And W is going to be the worm population. The robins eat the worms. The robins are the predator. The worms are the prey. This is going to be a predator-prey model. The predator eats the prey. There are also competing species models where each species competes against the other one for food. And there are also cooperating species models where they cooperate in some way for food, I guess. They go grocery shopping together. I don't know. All right. We want to write down a system of differential equations telling how fast the robin and worm population changes over time. A dr dt equation and a dw dt equation. A system of differential equations, they are ordinary differential equations. Here I'll call them ODEs because they involve ordinary derivatives. Now, one thing you could try is you could try just saying, okay, maybe, the robins, they got to have the worms around for food. And if there's no worms, maybe they die off because they only eat the worms. And the worms, if there's no robins, they grow, maybe exponentially. No predators that eat them. And that is the initial assumption that we make here. But it really is in saying that, it is really when the other species is not present that those are true. So we can't just write down an exponential decay here and an exponential growth here and say that we're done with it. We need some sort of interaction term representing, for example, if there's lots of robins and lots of worms, there's lots of eating going on, right? Lots of worms available to eat and lots of robins doing lots of eating and lots of baby making. So the robin population probably would be positively benefited by interactions between the robins and the worms. They're coupled together. I am going to use some constants again. The book in their examples doesn't do what I'm about to do, but remember, using arbitrary constants gives you a lot of power to model infinitely many situations at once. Flexibility, you could say. And also even understanding in how the parameters, the constants, might affect the answer. For clarity's sake, I'm going to use Greek letters for the constants. I'm going to call the constant of proportionality for the robin population in the absence of worms negative alpha. So I'm using a Greek letter, and it's got a negative sign to indicate it is a negative constant. Alpha itself would be positive, so that negative alpha is negative. Negative alpha times R. That is an exponential decay model if I didn't add anything to this. The robin population would decline. But I am going to add something to this that positively affects dr dt when robin and worm population is high. A positive constant, call it beta, times R times W. And if both R and W are large, then R times W is really large. If W is 0, then there's no worms for the robins to eat. This term becomes 0 and they decay. Also, if R is 0, both terms are 0 and dr dt is 0. If there's no robins to begin with, yeah, they don't just magically appear. Nobody is bringing them to the forest here. dr dt is also 0, and the Robin population stays 0. Do something similar with the dw dt equation, except when there's no robins, the worms grow. Alpha, beta, gamma is the next letter. That fish kind of symbol is a lowercase gamma. Gamma times W, representing exponential growth if there's no robins. But the robin population has a negative effect on the worm population. Negative constant, I'll use lowercase delta times R times W. So the R times W terms in both cases represent interactions. The alpha, the beta, the gamma, the delta, those are all unspecified constants that are positive. And we'd like to be able to think about what goes on here for arbitrary alpha, beta, gamma, and delta. Easier said than done. What we can start to do, however, is we can start to draw a phase plane. Phase plane. A plane labeled differently than usual, labeled with both dependent variables, an R-axis and a W-axis, representing robin population and worm population. For a given point in this plane with RW coordinates, the first coordinate would tell you the robin population, the second coordinate would tell you the W population. But those populations change over time, so the point's not going to stay where it is, it's going to move, so to speak. It's going to trace out a curve, a parametric curve, where there I mean parameter like t, time, with parametric curves from our past, not parameter as constant. Two uses of the word parameter, even within this one situation. Now think about this intuitively. If the forest starts out with no robins and no worms, and they're not trucked in, the population stays no robins and no worms. If you start at the origin, 0, 0, you got to stay there. It's an equilibrium point. Should I call it an equilibrium point or an equilibrium solution? Well, either is okay, but most commonly it's called an equilibrium point. It does represent two constant functions whose ordinary graphs are horizontal lines. R of t is always 0 and W of t is always 0. This one point represents those two solutions. There's never any robins and there's never any worms. If there's no worms, if W is 0, if I'm on the R axis, it's exponential decay, the R population should decrease, should move toward lower values of R. On the other hand, if you're on the W axis, where R is 0, there's no robins, the worms increase exponentially, upward pointing arrows. What about the case we're most interested in? Both R and W are positive. There are robins, there are worms. Are there any other equilibrium points? Yes, there is. To find the equilibrium points, take both right-hand sides, set them both equal to 0, and solve the simultaneous system of algebra equations. Let me give this one a name. I'm going to call it f of RW. And this one a name. I'll call it g of RW. Hey, these are both multivariable calculus functions. Nonlinear functions. In fact, I set both of those equal to 0 and solve the system for R and W. It's an algebra system, not a differential equation system. It's not the easiest system to solve, but it is solvable. And in fact, with these particular right-hand sides, the F and G, you do want to do a little factoring. With the f function, you can factor out a factor of r. And in parentheses, you're left with negative alpha plus beta w. And with the g function, you can factor out a w. And you're left with gamma minus delta r. For sure, in looking at this system of algebra equations, you see that one solution is r equals 0 and w equals 0, which we already knew intuitively. Solutions, and there's more than one of them, include the origin, rw equals 0, 0, and one more, given by when the things inside the parentheses are 0. Look at the first one. Negative alpha plus beta w is 0. What value of w will make that 0? How about alpha over beta? You can check it by multiplication. If w is replaced by alpha over beta, the betas cancel. You're left with negative alpha plus alpha 0. W is alpha over beta. What about r? Look at the second equation. What value of r will make that 0? How about gamma over delta? Gamma over delta. Where is that point? I don't know. Somewhere over here in the first quadrant. We got two equilibrium points. The location depends on what alpha, beta, gamma, and delta are. One key bit of insight this provides, doing this general situation provides, is it tells you if, for example, alpha and gamma are large compared to beta and delta, then these numbers are large, and the point is far from the origin. If alpha and gamma are large, if these two numbers are large compared to beta and delta, that corresponds to an equilibrium point far away from the origin. Equilibrium point meaning level populations, constant populations for both the robins and the worms. If, on the other hand, alpha and beta are large compared to alpha and delta and beta are large compared to alpha and gamma, these fractions are small, and the equilibrium point's close to the origin. The equilibrium solutions for both the robins and the worms is low, relatively speaking, as functions of times, as horizontal lines, which I'm not drawing here. What do the other solutions look like? It turns out they go around the origin about like this, and they come back to where they start. How could that be verified? It's difficult to verify it by hand. They're not exact circles either, but they do represent oscillations. The populations ultimately oscillate up and down. When there's lots of worms for the robins to eat, it's a feast. Robins are eating all these worms really rapidly, having lots of babies. The growth rate of the robins is large, but then they're eating lots of worms. The worm population goes down. And then when the worm population is low, then there's not much food for the robins and they start dying off. And then the worms benefit from that, and the cycle repeats. These closed curves represent oscillatory solutions as functions of t for both the robin and the worm population. But how would you know that's what they really look like? It's difficult without technology. Let's end class today by using Mathematica here. Let's define f and g first. And it turns out to be best to make the parameters alpha, beta, gamma, and delta be subscripts. This is a bit of a pain, but it can be done. I press the subscript button, and I'm going to do alpha underscore, beta underscore, gamma underscore, and delta underscore to escape D, escape for the delta, for example, of R underscore W underscore. This is the right-hand side of the Robin differential equation, negative alpha times R plus beta times R times W. Do something similar for G with appropriate modifications. Change the F to a G. Change this to a positive gamma. Change this to a minus delta. I have now entered the right-hand side functions for the system of differential equations. What do I do with these? I could try using dsolve value. Just for the sake of doing it, I will do it and show you it doesn't help. Yes, thank you. This should be a W. Enter those. If I try to solve the differential equation, this is the way you would want to try. I'm not really explaining it, but hopefully it makes some sense. You see the derivative, you see the double equal signs, you see the F and the G. You need to specify R and W are functions of T inside curly braces, and I could give it initial conditions. I could even pick particular numbers if I liked, like 1 and 2. I can type. And try to solve for R of T and W of T simultaneously. Well, guess what? Mathematica just gives up. I don't know what to do. It's too complicated. And you wouldn't be able to do it either. No human can do it. In fact, the answer is probably some non-elementary function, a function you've never heard of before, that kind of thing. But we can make the vector field, which is a generalization of the slope field. With slope fields, we put a 1 comma the right-hand side function, but we don't do that here. We put both right-hand sides, the F for the first one, and then the G for the second one. No underscores anymore, no T's anymore. R goes from, say, negative 0.5 to 5 or something. W goes from negative 0.5 to 5. If I'm going to see anything, though, I need to specify the values of alpha, beta, gamma, and delta. I could define them ahead of time, or I could put this inside a manipulate. Manipulate and allow them to change that way. Maybe all starting at 0.1, going down as low as 1 and going down as low as 0.1 and as high as 10. That's the syntax for alpha. I'll copy and paste it and modify it for beta, gamma. This seems like it might be crazy complicated, but this is worthwhile. So I'm going to get an animation that's going to allow me to change the values of the parameters, and I'm going to see arrows indicating directions of solutions. These are effectively velocity vectors for solutions, is what these arrows are. And for example, if I change alpha, if I increase alpha, the vector field changes, and you can see the point where there's an equilibrium, which is right around here, where there's kind of a tight rotation, is moving away from the origin. It also moves away from the origin if I increase, what was it? The delta or the gamma? Yep, moves away from the origin. If I increase beta or delta, it moves closer to the origin. The origin's right around here. Okay? And yes, you can kind of see the other solutions are going clockwise around this equilibrium point, representing oscillatory solutions for the robin and worm populations.